Maybe we can start now. Okay. So good morning, everyone. Today's talk will be on optoelectronic properties of InAs QD heterostructures, and it's a pleasure to have have with us Dr. Jhuma Saha. And so before starting the talk, I'll give a brief about her academic career. So Jhumadi did her MTech from ISM Dhanbad, and after that she did her PhD from Center for Research in Nanotechnology and Science, IIT Bombay. And then she finally joined PIFR, currently working as a postdoctoral student in nanoelectronics lab. So yeah. Hello? Sorry. Okay. So now I'll let Jhumadi start her talk. So Jhumadi, it's over to you.
Yeah. Thank you, Akash, for this nice introduction. So I'll share.
Yes, please.
I think you can see my screen, right?
Yes. It's visible.
Yeah. So good morning, all. So my title of the presentation is Enhancing Optoelectronic Properties of Quantum Dot Heterostructures through Strain Coupling, Modeling, and Characterization. So this was in fact my PhD thesis title. So I will discuss some highlights of my work in this presentation. So here is the outline. So I will start with the introduction, motivation, and discuss two basic works of my PhD. So first is this study of arsenic-based capping materials on single layer indium arsenide quantum dot structures. And second is this investigation of type 1 and type 2 band alignment on bi-layer indium arsenide quantum dot structures. And at then I'll conclude. So starting with the introduction, we know that fiber optic communication is conducted in a region where transmission loss is minimum. We know that for communication, we use this O band, which is around 1300, and S band, which is around 1500 for telecommunication purpose, as the transmission loss is minimum. However, people are moving towards this L band, that is the long wavelength region, because to meet the increasing bandwidth requirement for long distance communication and for high speed data transmission. Now, to work in this long wavelength region, we need sources and detectors such as lasers and detectors which can detect at this long wavelength region. Now, in the market, there are the sources and detectors. However, these devices based on quantum dots are very popular, and let us see why it is so. So we know that when we go on increasing the confinement from like if we start from the bulk, if we confine it in one direction, we get a quantum well. And if we confine in another one direction, we get a quantum wire. And if it is confined in all the three directions, we get quantum dot, and which results in this discretized energy states. And because of this discretized energy state, there are certain advantages of quantum dots. The first and foremost important advantage is its band gap tunability of quantum dot size, which means if we can tune the size of the quantum dot, we can tailor this band gap, and which is reflected in this emission wavelength. Means accordingly, if the band gap is high, we will get a blue emission, and if we can tailor the quantum dot like a bigger quantum dot we can do, then we will get a lower band gap and therefore a red color emission. Another advantage is its normal incidence operation, which makes it very simple for optical configuration. And the third is due to the discretized energy states, the electron and phonon scattering is very minimum in this quantum dot. And due to this minimum scattering or very less scattering, the dark current in the devices are very low, and which leads the devices to operate at a very high temperature region. Now let's see how this quantum dot are prepared. So there are three main ways of preparing quantum dots: lithography, colloidal synthesis, and epitaxy. In epitaxy, there are again two, that is pattern growth and self-organized growth. We will focus in this self-organized growth. So there are three modes of this self-organized growth. First is this Volmer-Weber, where a direct 3D island growth takes place. Means when you deposit a layer of film on the substrate, direct 3D island growth takes place because of the higher lattice mismatch between the deposited film and the substrate. For example, metals on silicon oxide. Second is this Frank Vanderwey-Merwe, where a layer by layer growth takes place. Because of the lattice matching of the film and the substrate, for example, silicon or gallium arsenide or gallium arsenide. So here it is layer by layer growth. Now third is the Stransky-Krasnov, where it is the combination of these two both modes. That is, first a 2D layer growth takes place, and after a certain thickness, a 3D island growth takes place. So it is also called a 2D plus 3D island growth. For example, indium arsenide on gallium arsenide. And we will in my PhD, this Stransky-Krasnov mode has been used to grow like indium arsenide quantum dots on gallium arsenide substrate. So there are several materials used, for example, indium arsenide, gallium arsenide, and certain alloys such as indium gallium arsenide, indium aluminum gallium arsenide. In the right side, you have seen this famous figure, which is this band gap versus lattice constant. So depending on the lattice constant of a particular alloy or particular material, we use those materials in this quantum dot system for different applications. We will see how we use it. Now, how these quantum dots are formed. So as I said, indium arsenide quantum dots on gallium arsenide substrate. So the lattice constant are different of both these materials. Like for indium arsenide, it is 0.605 nanometer, and gallium arsenide it is 0.565 nanometer. Now, when we deposit this indium arsenide material on gallium arsenide, we see there is mismatch in the lattice, right? So when we deposit, there is a strain developed when we deposit the indium arsenide on gallium arsenide. So when the indium arsenide atoms tries to adjust with the substrate atoms, so in that process it stretches itself and there is a strain developed, and this stretch can be done up to a certain layer, and that we call as weighting layer, and the thickness we call it as critical thickness. So this stretch can be up to certain thickness, and after that the strain releases. As we stretch a rubber band, we can stretch up to a certain moment and then it just breaks. So similarly, so this stretch is up to a certain point, and after that the strain relaxes and the island formation takes place. Now to maintain or to preserve this quantum dot, we cap it with a certain material. Here I am showing the gallium arsenide. So this is the quantum dot which is formed. This is the weighting layer, the substrate, and the capping layer. Okay, so this is the process how a quantum dot is formed, and we will see what different kind of materials that we are used for capping layer and how it affects the properties. So as we have seen, there are several advantages, but there are limitations of quantum dot based devices. So first is this non-uniform dot size distribution. When these quantum dots are formed, so it is not necessarily that the size of the quantum dots will be uniform. So there are non-uniform dot size, and which leads to multimodal PL. Multimodal PL means multimodal photoluminescence spectra. We get several peaks, which are not desired. Since we want to use this for laser or for photodetector, we want a particular wavelength. So this is not required, and due to this, there will be a line width broadening and therefore lower absorption. Now to solve all these problems, people do multi-layer strain coupled QDs, where several layers of quantum dots are grown and they are coupled to the lower quantum dots via strain. And this method, we have seen that we get a monomodal PL, means only one peak, and therefore narrower FWHM and higher absorption efficiency. So we will see I have included this strain coupled QDs in my presentation, that how it affects. So yeah, so let us see the study of arsenic based capping on single layer indium arsenide quantum dot structures. So why this capping is important? So the covering of quantum dot with a proper capping material is very crucial as it maintains its shape and size, and also it helps in strain relaxation, because if the strain will not be relaxed and due to higher strain there are defect formations, and this affects the intensity of the photoluminescence. Okay, now these two materials that I've shown, that is indium gallium arsenide and indium aluminum gallium arsenide, so these are two very popular capping materials which are used to cap the quantum dots. So indium gallium arsenide, it is known as strain mitigating layer. Why? Because so the quantum dot is indium arsenide and the capping layer will be indium gallium arsenide. So it helps in preserving the shape of the quantum dot and the size of the quantum dot, because it does not allow indium to go out of the indium arsenide quantum dots and towards the like gallium arsenide top capping layer. Okay, so it avoids or it prevents the diffusion of indium from the indium arsenide quantum dot, thus maintaining its size, and also it's therefore it acts as a strain mitigating layer. And second is this indium aluminum gallium arsenide, which acts as a phase separation alloy, because it the aluminum it sticks to indium arsenide quantum dot and it does not allow at all to indium to go like outside of indium arsenide quantum dots, and gallium to come inside indium arsenide. So it acts as a phase separation alloy. It separates this to indium arsenide and gallium arsenide. Okay, so these two materials are being used. However, the novelty in my PhD was nobody had used this indium gallium arsenide and indium aluminum gallium arsenide together as the capping material. So here are the 5 different grown heterostructures. So sample A, B, C are conventional. Conventional is this gallium arsenide, and people have used this indium gallium arsenide, indium aluminum gallium arsenide. So and these two are new, like sample B2 and C2 are new, or the proposed heterostructure with the combinational capping. So here so B2 is the first layer is indium gallium arsenide and second is indium aluminum gallium arsenide, and here it is just the opposite. And you will see the capping material is constant, like it is 50 nanometer in 50 nanometer in all the heterostructures, and like in sample B the 5 nanometer is in gas, I'm calling it is in gas, and in enal gas it is also 5 nanometer, but in combination these two materials are being divided into 2.5 nanometer each. This is the transmission electron microscopy images of the quantum dots. So these three are like sample A, B, and C with gas cap, in gas, and enal gas cap. We can see the quantum dots. So the quantum dots that are formed are truncated. They are in the shape of truncated pyramidal size. And we have measured like 15 to 20 quantum dots. And then we have just concluded this average dot height and the base width. Okay, so we see that with in-gas and enal gas capping, the dot dimensions have improved as compared to this only gallium arsenide capping. And in sample B2 and C2, if you see, so there are uniform dot size, and the sample C2 has a larger dot size dimension. You can see here. So, and these are even bigger than the sample ABC. So sample B2 and C2 had higher, the bigger dot size as compared to sample ABC. And this is because of the lattice mismatch, means this is because of the lower strain, and you will see why. So if you see this diagram in the right side, lattice mismatch percentage versus these two samples, sample B2 and C2. So here you see, so this is like a band diagram kind of a thing. So 1, 2, 3, 4 is indium arsenide. So this is indium arsenide quantum dot. The first capping of sample B2 is in gas. Second capping is indium aluminum gallium arsenide, and this is gallium arsenide. And for sample C2 again, this indium arsenide capping is enal gas because the band gap is higher, so therefore it is a higher. And then in gas, and then gallium arsenide. Okay. Now, if you see the lattice mismatch percentage, so the lattice mismatch percentage has been calculated like between both the materials, and you see the overall lattice mismatch in sample C2 is less as compared to sample B2, and this less strain, it helps like in large dot size dimension, and it will also like the defects or dislocations will be less in sample C2 as compared to sample B2. And here is the photoluminescence result. So we see that as we do the capping, like as compared to the gallium arsenide capping, all the other cappings, they give longer wavelength emission. Where and sample C2, which was like first capping is inal gas and second is in gas, it gave us the longest wavelength emission, that is around 1350 nanometer. So these combination capping materials, or the sample A, B, C, B2 and C2, so they were like used in a detector also, means they were grown in between like n plus gas contact and both, and this is like NIN structure, and a device was made, and you can see the dark current. When the dark current were measured, so we see the dark currents of this combination capping were very low as compared to sample B and C. And sample C2, I'm showing the spectral response of sample C2 because other samples were very noisy, the signal to noise ratio was very low, and sample C2, it gave the spectral response up to like 90K. After that, the signal was very poor. So it gave, so there are three peaks we can see, around 2, 2.5 and like 5 micron. So it is around like mid IR, mid infrared region. It gave us response. So with this combination capping, we have seen that it helps in reducing the strain. So therefore, a larger quantum dot size and therefore longer wavelength emission. So with this combination capping, we were able to get an emission around this O band, which can be used for the telecommunication purpose. But we want the emission towards this L band. So our main aim was to achieve this 1600 nanometer emission. So for that, moving towards this investigation of type 1 and type 2 band alignment on bilayer quantum dot heterostructures. Now, why bilayer? Why do we need bilayer? Why not single layer quantum dots? Since single layer quantum dot, it suffers from various disadvantages. The first is only a single layer, so therefore there will be low absorption coefficient, therefore larger FWHM. And since it is single layer and it is self-assembled growth, so we have very less control on the size of the quantum dots. And to improve this, we can grow a bilayer where this upper dot layer, the size of the upper dot layer can be controlled by this lower dot, like via strain. So the barrier thickness between these two materials have to be decided in such a way that there is strain. So above this lower quantum dot, the nucleation sites are formed, and just above this lower quantum dot, the upper quantum dots are formed. So therefore, we get better homogeneity in dot size, and therefore very good thermal stability. And therefore, since the size of these quantum dots are bigger, since already there is strain present, therefore the size of the quantum dots are bigger, and therefore we can get a longer emission wavelengths as compared to the single dot. Now, only this will not solve our purpose. So what we have thought, we thought of including antimonide in the capping layer. Since this antimonide, gallium arsenide antimonide capping, it acts as a strain reducing layer. And also by changing the, by changing the concentration of antimonide, like here I have shown. So by changing the concentration of antimonide, at certain percentage, the band alignment is like type 1, and beyond a certain percentage, the band alignment changes to type 2, and which helps in achieving the longer wavelength emission. So before going to this, so what we have done, we did this simulation with a single layer quantum dot so that we can check at which percentage we can get a type 1 and at which percentage we can get a type 2 band alignment. So this is a single layer quantum dot with a 6 nanometer of gallium arsenide antimonide capping layer. And here we have done a simulation and matched with a paper. So the percentage, antimonide percentage was varied as 10, 14, 17 and 22, and we got a very good match. So the average error was only around 2.5 percentage. And we have seen the energy band profile. So all the simulations were done using a Next Nano software. So we have seen that with like 10% and 14% antimonide, the band alignment is of type 1. And if we increase this antimonide beyond this 14, so this band alignment changes to type 2. Now, so by this simulation, we were confirmed that 10% will give us type 1, and 22 or 20% will, above 17%, it will give us type 2. So with this conclusion, we proposed a new kind of heterostructure, that is with a bilayer, that is bilayer quantum dot. That means there is 2 layers of quantum dots which are capped with gallium arsenide antimonide. And here 6 set of samples were grown. So with three S1S2S3, the antimonide percentage was 10%, and S4S5S6, the antimonide percentage was 20%, and the capping layer thickness was varied to optimize that which capping layer will be best. So it was varied as 2, 3, and 4 nanometers. And the distance or the thickness or the barrier between these two quantum dots was 6.5 nanometer, which was fixed in all the 6 samples. And these were grown at UCLA since IT Bombay doesn't have this antimony system. So these are the TEM measurements. We can see a 2 layer of quantum dots in all the samples. So ABC are with like samples S1, S2, S3, and DEF are S4, S5, and S6. And here are the dimensions of lower quantum dot and upper quantum dot. So we can clearly see here that the dot dimensions are larger as compared to what we have seen in the combination capping also. So here the dot dimensions are larger, and the upper dot dimensions, as I said, since it is strain coupled to the lower quantum dot, so the dot size of the upper quantum dot are bigger than this. And if you compare the S1, S2, S3, and S4, S5, S6, we see that the S3 among S1, S2, S3 with a higher capping thickness, it had a bigger dot size, and among this S4, S5, S6, S6 had the bigger dot size. And to confirm, sorry, so the photoluminescence, this is the low temperature photoluminescence measurement. We see that this S1, S2, S3, it gave us like around the S3 was the longest wavelength emission that we achieved, and it was around 1300. Whereas the S4, S5, S6, which we think that these are type 2, and therefore they gave a longer wavelength emission, and among them, S6, it gave us around 1500 nanometer. So this was a low temperature emission measurements. Now to ensure that whether it was type 1 or type 2 means alignments, from simulation we knew that 10% and 20% will give us type 1 and type 2, but we can also confirm this from a power dependent PL measurement. So here the power was varied, power of the excitation source, that is laser source, was varied, and the PL were measured. We can see that the S1, S2, S3, by varying the power, the shift in the PL is very minimal, means a negligible shift. Whereas in S4, S5, S6, there is a significant blue shift. So we have calculated slope. You can see the slope is very high in S4, S5, S6, and this is because since, as I told, as the type 2 alignment, it has a type 2 kind of band alignment. So there is a triangular potential, and with power, the energy in triangular potential, it varies as a cube root of power. So as we go on increasing the power, so energy will like shift. It will shift down and it will shift up. Therefore, we get a blue shift. So which we can see clearly in this S4, S5, and S6. So from here also it was confirmed that this S4, S5, S6 were having a type 2 kind of band alignment. So these all samples were also, we also did a time resolved photoluminescence measurements where we can measure the carrier lifetime. So we can see the lifetime of S4, S5, S6 samples. The lifetime is higher as compared to S1, S2, S3. And among them also, the S3, which has a like 4 nanometer capping, it showed higher lifetime, longer lifetime as compared to S1, S2. And S6, it showed longer lifetime as compared to S4 and S5. So average lifetime of the type 2 samples were higher as compared to the type 1 sample. And this is the room temperature measurements of, since I'm showing here only S3 and S6 as these were better among their sets. So we can see that S3, it gave us around like 1400 nanometer, but this S6 with 4 nanometer gallium arsenide antimonide with 20% antimony content, it gave us around 1680. So which was our main achievement, that is we got our photoluminescence around this L band, which can be used for various communication purpose. So in conclusion, I can say that how we have enhanced the quantum dot, the characteristics of quantum dots. So first, we did it with the combination capping by combining the two capping materials, that is InGas and indium aluminum gallium arsenide. So these two materials were used to reduce the lattice mismatch, to improve the strain so that the dot size could be improved, and therefore we got an emission around O band. And with this type 1 and type 2, that is by including antimony in the capping material and by varying the content like 10% and 20%, we were able to achieve, like with 20% and with type 2 band alignment, we were able to achieve an emission around this L band, that is 1680 nanometer wavelength. So yeah, so these were the two main highlights of my work. Thank you. So if you have any questions, I will answer.
Thank you, Jhumadi, for this wonderful talk. And now we'll start our question answer session. So if anybody has any question, he can unmute or unmute himself or herself, and then, or maybe he or she can write that in the chat box, and we'll ask Jhumadi to answer that. So anyone has any questions, you please can unmute yourself.
I can't unmute, somebody saying.
Okay, so I think we as hosts and co-hosts have to give them permission to unmute. Wait, it's Dibushankar, right? Yeah. So I have asked him to unmute.
Yeah, can you hear me?
Yeah, you're audible. Go ahead.
Yeah. Okay, so I have a couple of questions. First thing that I missed due to my internet connection probably, that why you told that they will have less thermal noise in these quantum dot systems?
Yeah, because see in the quantum dot systems,
sorry to interrupt, Jhumadi. Can you share your screen so that I think the screen share is stopped. Okay, yeah, thank you.
Yeah, so the noise will be less because see the quantum dots energy states are discretized, right? So the amount of energy an electron takes to like cross this energy states is higher than the thermal energy or the phonon energy. So therefore the noise will be less here, or the scattering will be less here.
Okay. And other thing is, you showed some PL, probably the next slide, some PL spectrum of different dots. Yeah. Yeah, this one, right? Yeah. So, do you observe any? What about the width of the PL spectrum? Because that is also, neat, right? As you were saying, the C2 is the base device, so I don't see any significant width difference between these different systems. So, is it there or?
Yeah, so the width difference was not so much significant. It was around only 2 nanometer. Means, for example, if this was like around 45 nanometer of width, so it was around 43.
Okay.
So and it was not so much significant here.
So is it important that you make it sharper and sharper?
Yeah. So it is important for like certain applications, for if we want to use it like for source, right? So we need this width to be as sharper as possible. So since these all these quantum dots like luminescence what I've shown, they are single layer. Okay, so in single layer quantum dots we cannot control the size significantly because these are self-assembled. So like the size can be controlled here only by like substrate temperature or pressure. So here therefore, so this system or these quantum dots should be optimized. Like since here only the single layer quantum dots, if we would have grown like multiple strain coupled quantum dots with combination capping, so that might have resulted in much sharper line width.
Okay.
Yeah.
And in some slide you showed like spectral response of quantum. So what actually the measurement is that in spectral response?
So spectral response is basically means that is a like a device response, since this is like only the active layer. Okay, means we call this like PL sample, but spectral response like when we have two contact layers. Okay, so we shine a light to the sample and then we see. So spectral response is basically, it is like a infrared photodetector. Means if a material is kept and the radiation, if it comes around like 2 or 2.5 or 5 microns, then it can detect. That is the spectral response.
Okay. Okay. The other thing is that you finally showed that you S6 sample. There, I mean, the other category is like type 2 quantum well. But don't you think that that will be inefficient to operate? Like if it is type 2, then as a detector will not be inefficient.
Means why you are saying so?
Because okay, my conception is like in indirect band gap, this is inefficient absorption and PL, but in type 2 the same thing happened, right? I mean
Yeah, so yes, so these can be like there is a trade-off, means what in which application you want to use, right? Because here the since type 2 the recombination will be little bit late, means it
right.
won't be a faster recombination,
Yeah.
right? And that you can see here also, therefore it has a like higher lifetime. So this can be used in case of detector but not as source.
Oh, I see.
Okay.
Sorry.
Yeah, so to make it like more efficient, the lifetime will be low, but then again if you see there are a lot of noise also. So again this structure or this heterostructure has to be optimized further, because because this was the heterostructure that we proposed, and it was not grown, as I said, at IIT Bombay. So they had grown that these structures with their parameters, right? We have certainly gave them how much material or what will be the composition, but then again the growth temperature and pressure they have handled. So when these systems we can grow, or we have to optimize these, like what should be the substrate temperature and the thickness also. As I said, thickness between the two dot layers here we have taken like 6.5 nanometer. And if you can see in these STEM images, there are defects, right? So there are these stacking fault, we call them as stacking faults. These defects, there are certain defects, and therefore we see this wavy nature in the PL spectra. So this has to be optimized so that we can use these as sources, so that the photoluminescence should be of like high intensity.
Okay, thanks. That's all.
Yeah.
Anybody else has any questions? You can raise your hand or you can write it in the chat box, as Shomok said. So, Jhumadi, can you go to that slide where this dark current is written? I just didn't understand what is this. Why is this called dark current?
Because this is like in the absence of light, means here we like this is dark current and this is photocurrent. So spectral response is basically the photocurrent. Okay. And this is like in absence of light, we are measuring the current. So are we getting any current? So the current which we got from like C2 was very less, very less.
I see. Okay.
So we should not get any current. No light is shown.
Yeah. Okay. So I think no one has any questions. Okay, Amit Basu. Okay, Amit, I'm unmuting you. Okay, you can unmute yourself.
I have a question that can you just
Amit, you are not that much.
Yeah.
Amit, you are not audible properly.
Yeah. Can you hear me? Can you hear me now?
Yes, yes, yes.
Yeah. Can you just go to that slide that with the change of the concentration of antimony, how the type 2 devices are forming?
Yeah, this one.
Yeah.
Amit.
No, with the change of yeah. Yeah, in the bilayer, yeah.
Bilayer, okay.
Yeah, this one. Can you explain this for bilayer?
Okay. Yeah. So in the bilayer also, I have a slide which I did not include. Wait. I think so. No. So in the bilayer also, when you put the antimony as 20%, right? So the band gap will be, the band alignment will be a type 2. Means it's not clear what you are asking actually.
Amit, can you repeat your question again?
Yeah.
Amit?
Hello?
Yeah, Amit, can you repeat your question, please?
Can you hear me now?
Yes.
Yeah. The change in the I'm just asking that why with the change in the percentage of the antimony in the slide that you have drawn the band structure. Yeah, the second hump is rising with the change in the antimony percentage. Can you explain that why this is happening, sir?
Yeah. So this band diagram, it is basically so this. Yeah. So this hump. So this is you can see the pointer, right? So this is basically the quantum dot. Okay. So this is like gallium arsenide region. This is quantum dot. This is the antimonide capping, and this is again gallium arsenide. Okay. So when the antimonide percentage is less, so this is like a type 1 kind of a band alignment, and but when it increases, this changes to type 2. You are asking why it changes to type 2.
Amit, is that what you are asking? Yeah, he's saying yes.
Yes, exactly.
Yeah. Okay. So when we increase this concentration of antimony, means I'm not sure actually means the exact thing. Means I'm unsure. Means I have to see this. Yeah, I can like. We can discuss it later if we.
Yeah. Maybe Amit, Maybe Amit, you can later discuss with Jhumadi and clarify your conception.
Yes.
Any other questions? You can please raise your hand. Okay, Shikhar Gupta.
Hello.
Okay. Yeah, Shikhar.
Can you explain how you control the thickness of when you grow this crystal? How do you control the thickness of this quantum dot? initial slide, like when you were lattice mismatch was there, how do you control the height of the crystal?
Yeah,
Yeah, yeah, yeah.
this you are saying, right?
Yes.
So before growing this, so we measure the flux, okay, like how much monolayer, means how much monolayer we are like, we call it in terms of monolayer, okay. So one monolayer is like lattice constant, half of the lattice constant. So before growing these materials, so there are certain measurements which are done, like at which flux, how much like material will be grown. So at that particular moment, like we know that with this much flux, means this much flux per second, this much material is going. So first that measurement is done, and after that only we fix this. Like indium arsenide, we grow, like we fix it, means it has been optimized and it has been fixed at 2.7 monolayers, okay. So when we grow the quantum dots, so 2.7 monolayer is fixed. And before this means when we like grow this 2.7 monolayer, before all these measurements, the flux is first measured, like how much will be the flux of indium, how much will be the flux of arsenide, and with how much minute or how much second this much material will come out of the system. So that is measured first, and then only we, by that only we control. Yeah.
Okay, is it fine, Shikhar? Or you have any other queries?
Okay, so like okay, so there's a limit to how much we could grow the crystal, or like uh,
Yes, means limit in the sense, means you want to grow up, means this is a controlled growth, right? Means we cannot go on like since I'm saying like 2.7, we cannot go on like releasing the materials and grow like very bigger quantum dots. Means as I said, like if we get a bigger size quantum dots, so we will get a longer wavelength emission. So again, there can be question that why you grow only 2.7, you can grow 3, 4, 5. So then that will not be a controlled growth, that will be an uncontrolled growth, and there will be like incoherency in the dots, because if you, because then add atoms will be coming, okay, and like small quantum dots will coalesce at and give a bigger quantum dot, and again there will be some add atoms which will be lying, and they will create defects, okay. And here when we talk of this like quantum dot systems or quantum dot heterostructures, which will be used for lasers of quantum dot, there won't be only single layer. There will, when we grow the device, there will be into 30. So the single layer quantum dots will be 30 layers grown. So if we cannot control the defects at the like when we are growing the first layer, so those defects will propagate. So these are like controlled, and we fix the, there is a limit, yeah. So there is a limit, we, because since these are all controlled groups, we cannot go on
okay,
adding the
so
materials, yeah.
when we reach the limit, this quantum dot appear, like when I saw the picture, it was like not it was just spreading.
Means the,
Yes, yes, yeah, yeah. This one, the previous
okay.
slide, yeah. So
Hmm.
after some point, it's just spread, so it doesn't contract itself.
Means there will be strain relaxation and those islands will be formed, okay. And if
Okay,
there won't be any control, then the defects will also be formed. Means there will be bonds like as you are seeing here, and those
okay, so
defects will act as trap centers, and they will like diminish your luminescence.
okay, so this quantum dot is a like control defect. Like we are introducing it.
Yes, these are defects, but these are control defects, yes. Yeah, any other questions? Yes, somebody I think wrote in the chat box.
Okay, so anybody has any other questions, you can please raise your hand and I will ask you to unmute and then you can ask. Okay, so I think no one has any further questions. So we'll end it. Thank you, Jhumadi, for this wonderful talk again. And thank you everyone for joining us in this journal club talk. And yeah, so we'll end it now. Thank you all again.
Thank you so much.